We're going to take a look at angular momentum and angular momentum conservation as it pertains to some generic problems that we see in AP Physics. First off, we already know about linear momentum as the tendency for an object to want to keep moving. It wants to resist changes in its velocity, wants to resist an acceleration. Angular momentum is going to be the same thing, but just for objects that are moving in a circle somehow. Either a discrete particle on a string, maybe swinging around, or possibly a disk that is rotating, or figure skate, or anything like that. And where we have in linear momentum mass times velocity, where mass represents some sort of inertial quantity, and the v represents some sort of speed or rate of change of position. In angular momentum, we're going to have a similar setup. We're going to have L is the quantity that we're going to use to represent the angular momentum. And I like to think of it as L because when you draw an angle sort of symbol back in geometry, it looks kind of like an L. But we use L for angular momentum, and it's also going to be an inertial quantity, but in this case, the rotational inertia. And it's going to be multiplied by a speed quantity, but in this case, the angular speed. So it's going to be just a direct swap over, like so many of the other angular problems that we've had in the past. The one thing that's going to be interesting here, I mean, aside from just calculating the stuff, is that if you wanted to get some sort of change in momentum in a linear problem, an outside force had to act on the object in order to change its velocity. That could be from an impact, it could be from a collision, two things sticking together, it could be anything. Rotational inertia, however, well, it's got multiple variables inside of here, because if we just think in terms of, let's say, a discrete particle, the I value for that is equal to mass times the radius squared. And if we were to find the angular momentum, I'll just do it as magnitude here without any vector hats. For a discrete particle, it would be mr squared multiplied by omega. And that means that we have two quantities that could change in the problem. Normally, we think that the mass of the object stays constant, that's unless parts of it fall off. But the radius of an object could change, possibly, and the omega could change. So we're going to have some interesting conservation problems here where we have two variables that can be altered. Now, just in terms of calculating angular momentum, that's it. It's just anything that you want to say has angular momentum. You take its mass times its radius squared if it's a discrete particle or whatever the I value is for it, and you multiply it by the omega. If you're dealing with something that has a linear velocity given, we can also further substitute in that the omega is equal to v over r for tangential velocity. And then we could say that it's m times r times v, which is just mass times velocity. That's the regular or linear momentum the object has multiplied by its radius. So we have another one of those situations where an angular quantity is just a linear quantity multiplied or divided by a radius. So that's kind of nice to know. But let's take a look at some of the ideas of conservation. We'll take a look at a little video here first. And this video is from Physics Demos, the YouTube channel. And in this case, there's a professor with two heavy weights in his extended arms, and he's going to rotate around on a platform. And as he does so, he'll have angular momentum. And he's going to move his arms in, and you can see that his velocity changes. And when he moves his arms back out, his velocity drops down. This is because his angular momentum is based off of his mass, the radius that the mass is at. So his body's going to have some rotational inertia on its own, but then the weights on his hands, they have a lot of rotational inertia because those masses are far out, and they're going to have some tangential velocity. Every particle does. So when the professor takes his arms and moves them in, he's decreasing the radius that the mass is at. And since there's no place for the momentum to go. We can't decrease the momentum of the system without it transferring to another object. We have to have the velocity go up. So it's kind of an interesting internal conservation of momentum type of problem. So down below, we've got some little definitions of this stuff. So conservation of angular momentum, just like linear momentum conservation, means that you have to have an isolated system. And in that case, total momentum gets conserved. If that isolated system for linear particles involves two things colliding with each other, bouncing off or sticking together, elastic or inelastic, you have to take into account those two objects. And it's just the velocities that change inside that momentum calculation. However, inside of an angular problem, you could have just one object, and its radius value and velocity values change inversely of each other to maintain the total angular momentum. So while in the linear problems you required two objects for a conservation problem, we can really say for an angular problem that we're really just looking at the total angular momentum initial equals the total after. It doesn't matter if it's one particle or two particles. So if I have written out here, the initial angular momentum can be I initial multiplied by omega initial, and the final angular momentum for a single particle or object can be IF times omega F. If the I value increases, so mass gets further away from the pivot point, omega will decrease like we saw with that professor. And if the I value decreases, then the omega value should increase. And these will be proportional to each other. So if I doubles, omega would be cut in half. Now, the second way that we can take a look at conservation of angular momentum is with collisions. We can have two things hit each other. So I've got a video over here from our favorite website, Pivot Interactives. Zoom in on this. I think we can see most of this video here. In this case, there is a wooden disc of large radius and then a black disc of smaller radius. They're almost the same mass though. And when the video starts, you'll see the wooden disc rotating pretty quickly. And when the black disc gets dropped on top of it, it seems like it all slows down quite a bit. This is a classic sticky collision sort of situation. You have one object that's pretty light rotating, and then you have a increase in total mass, which decreases the velocity. And we can watch this in a little slower motion. I don't know if that's going to be as illustrative as it could be, but you can see the particles moving. Sorry, particles. You can see the disks moving and the dots on them representing points on the object. And as soon as the black plate hits the wood plate, there's a decrease in angular speed. And we can calculate that, and we can figure out what the angular velocity should be when it's over. We can use the equations that we got right here up above in order to solve this problem. So let's go ahead and get some data from the Pivot Interactives and do a couple calculations and see how close to angular momentum conservation we've got. Moving into side-by-side mode so we can get a good view of both of the equation and the video at the same time. So we're going to use some tools here. We got a protractor that's already lined up to show angular positions there. We got a ruler here, which, well, that one's impossible to see. This one, there we go, the red one, that one's easier to see. So we can get some radius values for both of the disks, and from there we'll be able to calculate some stuff. So let's get rid of the ruler right now. We don't need that. Let's get the... Get this so we can see. Oh, there we go. Blue dots right on the thing. Let's go and get the timer going here. Click forward some frames. Sorry to drop the other disk. Looks like it's about half of a rotation at half a second. So we can use that to calculate omega. Let's get some space over here on the side. So we can say that omega initial is going to be pi radians divided by 0.5 seconds, which is 2 pi radians per second, which would be equal to, 6.28. And we can calculate what the I initial is for the wood disk. For a disk, the rotational inertia is 1/2 mass times radius squared. Up above, it says that the disk has a mass of 2.85. I'm not showing that on screen. And the radius here, if we pull that ruler back up, looks like it's exactly 30 centimeters, so we'll do 0.3. And if we calculate that out, we get 0.128 kilograms meter squared. So that's our initial value. So we can use that to calculate an initial angular momentum. Let's see what happens after they collide. Go forward a few more frames, wait till the disk hits and they're stuck together. Looks like they're together. We got the blue dot there again. Let's go ahead and reset. Let's go forward another half turn. If we can we make it to a half of a turn? Perfect half turn. So the final is 0.733 seconds. Which would give us an angular velocity of, I'm trying to use the correct number of sig figs here. Life is not treating me well on the calculator end of things. There we go, 4.26, I'm sorry, 4.29. So that's what we're getting at the end. And the rotational inertia in the final is going to be that of the wood disk plus the rotational inertia of the black disk, which they told us the mass up above is 3.06. Again, you can't see that on screen. And its radius appears to be 18, looks like, 0.18. Which gives us a combined rotational inertia of 0.178. Now let's see how close we are. We got two i's, we got two omegas. We'll calculate out what the rotational inertia, what the conservation of angular momentum is. Put a little question mark there. And we've got I for the wood, multiplied by omega I, question mark, does it equal I final times omega final? And if it's not exactly the same, we'll kind of see how close it is. But if we put in those numbers that we've got, this is a must-see TV right here. Let's calculate that out. And as you can see from the calculations I got up on the screen there, they do not equal to each other. They don't equal. In fact, they're a whopping 4.9% off. Oh, that's not bad. That'd be okay. It's less than 5% error there. So we're dealing with a situation where we got dots. The video is not great. In fact, back before they collided, the one dot wasn't quite there. If you let it go for 2 rotations, it wasn't quite 0.5 seconds per half rotation. It was a little bit less. So, it's not a perfect world. We're a little bit off in our numbers there, but this kind of demonstrates the point that it is pretty consistent with the idea that when things collide, total momentum has to stay conserved, and we can just take the total, instead of the total mass of 2 objects, it's the total rotational inertia of the 2 objects. Instead of their linear velocities, it's their angular velocities. So that's a little introduction to angular momentum and conservation. Remember, the key point that makes angular momentum different from linear momentum is that you can have a single object have changes in velocity just by modifying its own mass distribution. So that's all we got for this video. Have more for you guys another time.